Everybody okay on laminar flow and turbulent flow? Turbulent flow. Yes, no? Huh? And it talks about pressure occurs when there's a resistance to the flow of fluid, right? Already talked about that. Fluid area and velocity. This is the flow rate into a cylinder. This doesn't necessarily mean the speed of the cylinder. We'll look at that in a minute. So this is not exactly true. Everybody okay with force? Area. So we deal mainly with cylinders. And we went over there to the mechatronics lab and looked at a bunch of cylinders over there. So cylinders use a piston, and the piston is round, right? Understand that? So that's why we need to learn how to find the area. So what would be our pressures here? So how did we come up with this? So we got a 2.5, we got a cylinder that's got where the piston's got a 2.5 inch bore and it's got a 1 inch rod. So what would be my area for extending? So we extended on this side. So this we have 2.5 inch bore, right, on this side. And on this side, what would the area be? Well, it's going to be the area that we calculated there minus the area of the rod. So when our pressure comes in, Pascal's law says pressure is exerted exactly the same all through the space in here. And it's at 90 degrees. So this guy, the pressure is not pushing this way, which would cause it to retract. It's pushing this way, right? You understand? So what force we get to retract would be what is pushing against the piston, not against the rod, against the piston. So when we calculate the force we generate, the extend side would be able to generate more force than the retract side. And what would those be? Anybody remember how you do that? It sounds like really good test questions, right? So how would we do that? Yeah, so what we need to do is calculate the area first. So what is force equal to? What's Pascal's law assigned to math? So we're going to generate a force, and then we can rearrange this. So force is equal to what? Yeah, area times pressure. So first of all, we need to make up a pressure. So let's use 60 psi, which is pretty standard for using air tools, hand air tools, not the ones that we dig up concrete and that kind of stuff with. Those are going to use quite a bit of force. But if you got an impact wrench at your house and you got a compressor, usually we run them around 60 psi. So what would be my extend force and what would be my retract force? 60 psi. Guys, you're gonna have to have a you can see right off the bat, you're gonna have to have a calculator for this class. So we gave you the formula, we gave you the PSI, and then we gave you the bore, and then we gave you, what is the bore? Yeah, but what is the bore? What is the bore? You talk about the bore. The inside diameter of a cylinder, right? So usually when you go out and buy pipes, they size the pipe according to the bore, not according to the thickness of the wall. So it's not the outside diameter of the pipe, it's the what? It's the inside bore of the hole in the center. And then we have trade sizes too, so you know, there's a lot to learn. You know, when people say 2x4, have you ever measured a 2x4? It's not because it's a trade size, that's the trade size they would give it. It's actually 1.5 by 3.5. So pipes are trade sizes too. You could look those up. So how much force will be generated to extend? Well, first of all, I have to calculate the what? Okay, how do we calculate area? Area is equal to what? Well, not the area. What you're doing is what we're trying to do is we're trying to solve for force. So you say it's equal to area times pressure, but I don't know the area. I'm sorry. So you say area is equal to force over pressure, but we don't know the force. What we're trying to do is calculate the force, right? You understand? And I know two things to calculate the force. Now, once I've got the force, then I can calculate the area the way you suggested. But I can't calculate the area unless I know the what? The force. Understand what we're saying? Yes or no? So I can't say force is equal to area times pressure. And I said, okay, what's the area? And you say, well, it's the force divided by the pressure, but I don't know the force. All I know is the pressure. So I have two unknowns, right? You understand? So I can't calculate that. So that is a formula, but what two things would I have to know over here? I'd have to know the force and I would have to know the pressure. What do we know? We know the pressure. Okay, 60 psi. Well, I don't know the force. That's what we're trying to calculate. So we need to calculate the formula for area. What's the formula for area? Not using this formula right here. What's the formula for area? Yes, we could use that one, right? The actual formula is pi times r squared, power squared. And of course, we transposed this, and we went to area is equal to. So I can instead of the radius, I can use the what? I could use diameter. But see, that's going to be what? That's going to be pi diameter divided by 4 squared. Right? I mean 2. And then if we squared them, we could also say the area is equal pi, and we square both of that. That's going to be d. That's going to be d squared over 4. And then we can go ahead and take pi and divide it by 4, and it comes up and gives us 0.785. So this is the formula this is the formula we normally use. Of course, you can use any of those. So what can you use? You can use the area, whichever one you're comfortable with, would be equal to pi r squared. Or you could say the area is equal to pi times diameter divided by 2 squared. Or you can say the area is equal to pi times diameter squared over 4, or you can say the area is equal to diameter squared times 0.785. Any one of those formulas should give you the same answer. Of course, which one do I like to use? 0.785, because that's so much easier. But every one of those is a formula for area. So what would be the area of a 2.5 inch bolt? Well, I would say the area would be equal to 2.5 times 0.785, and that would give me the area. What's that? And that's going to be inches squared, right? So square inches or inches. That's the way we represent square inches. But you could use all these, so you could square the diameter. So let's do this. So I could come up here and I can say the diameter area would be equal to pi. It's going to be 3.14 times the diameter squared, which would be 2.5 divided by 4. And we would come up and get exactly the same number. So whichever one you're going to use, that's fine with me. But to me, once you get that 0.785 in your head, it's just so much easier to do. So 1.96, everybody okay there? Everybody okay there? So that would be what we're pushing against here. So down here we got 1.96 square inches. And so so anytime the fluid comes in on this side, we would push that way. And then to push it the other way, we would exhaust it, by the way. By the way, the name of this is called hydraulics pneumatics. And what you're going to see is basically most of the time, if that arrowhead is filled in, it means we're dealing with hydraulics. If it's not filled in, it means we're dealing with pneumatics. And the cylinders are basically the same. So what would be our push? What would be our retract pressure? Our retract area. So what would we have to do, guys? It's going to be what? It's going to be area extend. I'm going to call that area 2 minus area retract, right? Area of the bore, I'm sorry, minus area of the rod. So what we have to do now is calculate the area of the rod. What's the area of the rod? 0.785, right? I can do that in huh? Well, I'm sorry, you missed last week. You know, we had class last week, right? Huh? So what we got? What's our retract? Huh? So the area of the rod would be equal to what's the rod size? 1 squared times 0.785. Of course, 1 times 1 is what? Well, yeah. Then so the area of the rod is going to be equal to 0.785 in this situation right here. So my retract area is going to be equal to what? Well, no, we got to take 1.96 minus 0.785, right? Okay, so we're going to tract it at 1.18 square inches. So now how much pressure would we have to extend it? Well, we're going to have 60, because I gave y'all the 60, right? Let me get rid of some of this garbage. Yeah. So my force to to extend, my force would be equal to 60 times 1.96, and my force to retract would be 60 times 1.18. So what do we come up with? And what would be our force to Are we okay? Everybody okay? Let's know. All the cylinders that we'll be using over there are rodded cylinders, which means they got a rod in them. If you got a rodless cylinder, we looked at over there on the manufacturing line, that means you're extending to retract with the same, right? As far as the force that we generate.
Last week you were saying, compensation for, air room places. So you saying like the track, the track, like 1.1 more than that or less?
We would actually, the weight we could pick up would actually be slightly less than what we calculated because of the efficiency of the system. You know, there's no system that I know of that's 100% efficient. But when we do our math, we basically, so what we would do is we'd make sure we had more force than what's required to lift the load. Now, a rule of thumb, I would have to find that out. I'm sure there's a rule of thumb, like 10%, yeah, something like that, that if you didn't know the efficiency of your system, you could go ahead and increase it by that much. That's a really good question. I'll see if I can figure that out. Or I guess I could give you an assignment.
Well, I'll get something.
Yeah, well, that would be, you go out there and you do all your calculations. You don't want to lift up a 500-pound load. And you do all your calculations for 500 pounds.
Right.
And you go out there and it will lift it because you didn't take into consideration the efficiency of your system. And that's something that they're starting to, even on electrical motors. For years, they would give you this information, but they wouldn't give you the efficiency of the motor. And that's something that they provide now. That's required now on the nameplate of a motor. So here they were using 750 psi. And I think that this is where we left off on it. Yeah. And so this is they calculated. Like I said, this is where we left off last time, where we actually calculated. Of course, this is not at 60 psi. This is the same one. They're using 750 psi. And is this going to be different for pneumatics than hydraulic? Pressure's pressure. So pressure's pressure. So when it says force is equal to air times pressure, it says nothing about it being what? Which fluid you're using. Well, one has the ability to be higher pressure, but probably if you look in industry and see which one's used the most, probably not. Huh? Probably, especially in robotics and automated systems, we use a lot of pneumatics. What advantage does pneumatics have over? Well, and plus it's a lot safer. Pneumatics is a lot safer. Well, not even electronics, because normally we use in hydraulic systems we use an oil-based fluid. Or liquid, and of course, and what advantage does an oil-based liquid have over water? Water would work just as well. There are some hydraulic systems out there that use water. Rust, yeah, rust. Using your water pipes, you see that. Water pipes that have problems with. You got back in the day when they used metal pipes instead of PVC. Now it's mainly what we use. They're trying to get away with that because the problems we have with pushing water through metal. So we can go to instead of using metal piping with pneumatics, we can use plastic piping. Yeah, but even galvanized steel, the outside that's okay. Inside is yeah, PVC is great.
I ain't never gonna work about
Well, the gallon, you have the pipes, the size of the pipe. No, the size of the pipe determines the flow. What determines the pressure the pipe can handle would be the thickness of walls that keeps that keeps that bore in there. So the size of the pipe determines the flow or how fast things move. So that's why in water pipes you have a schedule 40 and schedule 80. What changed? The wall thickness. Yeah, so one of them's rated at a higher pressure than but we use lower pressures with pneumatics, and we'll look at that later on. So when you go out and buy a compressor, they're usually rated in two things. What are they rated? PSI. And what flow they can maintain. Yeah, so they're in a flow rate, and that's a pump too. Yeah. Of course, we know power is equal to work time distance, right? And these are some formulas that we're not going to say we're going to have to memorize them. We just need to be familiar with it. You know, if that little booklet, Nancy says you ordered it, by the way. Like I said, I wasn't responsible for ordering the books for this class. So she says you ordered it. I have to go back and look at the actual order, and why the bookstore hadn't got it, I don't know. 2 years ago, we turned our bookstore over to a private company. And we don't have hardly any control over.
It was like,
Huh? Yeah. So I was a personal friend with the bookstore manager. He would call and let me stuff all the time. We don't ever hear from him. But this is horsepower. Of course, horsepower is something that we use over here. And I think I've told y'all the history of horsepower, right? Yeah, well, the problem is when the steam engine first came out, people didn't understand. All they understood was what horses were. So that's what it was. The average horse could raise 50 pounds in 1 second, 500 pounds. Of course, now we're stuck with horsepower. The rest of the world is using watts or kilowatts. But basically, in ours, electric horsepower is about 746 watts per horsepower. And then hydraulic pressure is the formula down at the bottom. So this refers to, so it'd be PSI, so force times distance. Of course, here we're using PSI, right? You understand, pounds per square inch over here. What we call the U.S. customary standard. How fast it's moving. Over here we're using gallons per minute is the way we rate fluids. Liquids. What do we rate? Air. You can't say gallons. You ever got a gallon of air? Do we have a gallon of air? Cubic feet. Yeah, cubic feet. So we rate it in a volume. There's so many cubic feet per minute. Then we take that and we divide that by 1714. I have no idea where that number came from. I'm sure it came from some physics equation. And then we can multiply that times the efficiency of the system if we calculated it out. So usually it's around the PSI times the volume, right? So this is the hydraulic formula. I need to go back and add that too. If it was pneumatics, it would be gallons per minute. It would be cubic feet per minute. And then divided by 74.
Okay.
Yeah. Hydraulics is rated in gallons or liters per minute. And then air is managed. So we understand a gallon. A gallon is not a weight. A gallon is a volume, right? So it's the volume of fluid that you move past a point at any one time. So let me go ahead and, like I said, these are not, oops, I don't know why that's down there. So it says hydraulic or pneumatic, and that's not exactly true. So horsepower in pneumatics would be equal to what? PSI. Yeah. Yeah. we can do that too. That's probably better. Not squared. And then times efficiency. So there's probably supposed to be another parenthesis over here. Of course, I have to spell efficiency. No, I don't have a space up there. Okay, so that looks better. I need to go and update the PowerPoints up on Blackboard. I just now noticed that. Are we okay? Fluid flow rates. Originally, this was written down as the speed of the cylinder, but that's not exactly true. But this is the rate of the fluid flows. So velocity would be equal to what? Flow rate over area. Flow rate would be equal to the area times the velocity. And area would equal the flow rate over velocity. But you got to understand what decides which one of those formulas you use is depending what you know two things about. Just like Ohm's law. So electricity, our main law in electricity is called Ohm's law. People make this mistake all the time. So I come over here and I say, okay, you know, what's Ohm's law say? It says the voltage is equal to the amount of current flow times the amount of resistance in the circuit. And what variation of that formula you use depends on which you know two things about, right? So somebody called out a formula for area, but they said force over pressure. But the problem is that we didn't know two things. So this is another one of those formulas we can put inside a triangle or whatever you want to call it. I think the book, we use circles a lot, but normally I just do this. So flow of the fluid would be equal to area over the pressure, over the velocity. That's what I would do. So what we do is we just cover up what we want to solve for, and that would give us the formula. So what's nice about these little three-term equations is you don't have to know how to multiply. So in algebra, how do you learn how to transpose equations? Yeah, whatever you do on one side, you do the other, right? You understand? So what we learned here is that if you got a three-term equation, you can just put it in this little triangle or this little wheel, and you just cover up what you want to solve for. It makes transposing the equation really easy. It's actually L. It's a lowercase L, so that was, I thought I corrected that too. I'm working on these things about 3 different places, and sometimes I don't say when I make corrections. But, okay. The formula for speed is a little bit different, and we'll go back and look at that later on, the actual speed of an actuator. And what's an actuator? That's another term. By the way, we got a lot of terms in any trade. Every trade's got its own unique language, right? And I think we might have talked about it in this class, but I do this on every class, is that that's one way people know that you understand the trade, if you can speak the language of the trade. You know, if you go into a doctor's office and the doctor tells the nurse, give him about that much, like I said, what would y'all do? Just turn around and leave. Yeah, I ain't gonna be around this stuff. So what we've done, what I'm trying to do on most of my classes is set up a glossary. So if if you look on the Blackboard site, and I don't know if I would, probably next class would be good to print it off. This class probably wouldn't be, except toward the end of the term, because I'm in the process of writing. So everything you see in that thing is keyed in by Rich Raymond. So, but it would be a good place to go when you said know the meaning of these terms. Just look at some of those definitions. But it's in the course content section, I think in handouts. This is the rotary actuator or motor speed would be determined by something called a displacement. And what is displacement? Right, but basically it's how much volume or in multi-piston motors, it's usually how much you can move in a revolution. How much air you can actually move in a revolution. Are we okay? We went through this. Okay. And we already went through this last class. And this is about where we left off. Are we okay? So here they say flow rates. So hydraulic and pneumatic systems consist of three things, of course. We're going to have some type of source for our power, right? Then we're going to have some type of control of that power. And then we're going to output it. And this is pretty standard for any control system. Even my cell phone. What three things do we have on our cell phone? We got input, right? And then we got output. And we got something in the center which would be control. So of course in a hydraulic system we use our power source is going to be a pump. And in a pneumatic system our power source is going to be a compressor. So basically a liquid generates force when you use it. I mean a pressure when you use it. I said that wrong. And then a gas, we have to pressurize it before we use it, right? So we understand the difference. So what we do in pneumatics, before we can use it, we have to generate a pressure. So that's what a compressor does. A compressor generates a gas pressure, and then of course a liquid, all we have to do is push it against something. Power supplies, we have some, usually have to have so we got a pump and we got a compressor. So pumps don't create, they don't move on their own. Usually pumps are going to be some type of rotary type device, right? And most of especially pumps we see in hydraulics. And then of course compressors are going to be some type of rotary device. So that means normally we have to have some type of prime mover to move the pump. Pumps don't move, they have to have a prime mover. The most widely used prime mover, of course, is electric motor. Followed by what do you think? Combustion engine. Yeah, combustion engine would be the one that down below that. So we gotta have a prime mover. Then we're gonna have a pump, which is kind of, I need to do this PowerPoint. So what a pump does is converts a mechanical power into fluid, right? And then into a fluid power. And then a compressor does what? These are not my PowerPoints. There we go. Problem is we have with a bunch of these PowerPoints is that we originally taught hydraulics. Well, we did, all our labs were on hydraulics, and I think I explained that, and we taught pneumatics, and everything's changed over, but it's been quite a while since we've been doing it. So, okay? So a pump converts mechanical power to fluid to, a pump converts mechanical power to hydraulic power, and a compressor converts mechanical power into pneumatic power. I'll get this in a minute, guys. Okay? And we have there's a whole chapter, not a whole chapter, it's part of a chapter on compressors and pumps. Of course, you know what the actuator does, right? What does the actuator do? I corrected all these guys. So a compressor, an actuator converts fluid energy into motion to move loads or move things, right? The types of actuators we have cylinders. Everybody okay with the cylinder? And then we have what we call rotary actuators. And then we have what we call motor. So what's the difference between a rotary actuator and a motor? What's it say?
Rotary actuator.
Well, they move in an arc. They don't necessarily move in a circle. A rotary actuator moves in an arc. But a rotary actuator has a limited, what we call stroke. Stroke, and that's another term, stroke is the distance the actuator can move. So cylinders, you can see their stroke. The stroke is determined by the size of the cylinder and the length of the rod, right? The rod has to be longer than the cylinder, so it basically be the inside of the cylinder that would determine what we call the stroke. But a cylinder creates a linear or a straight line force, and then a rotary actuator creates an arc. But a rotary actuator has a limited stroke. It's usually less than 360 degrees. 180 is pretty standard. This is just going to swing and it's going to hit against something and it's going to stop. So a rotary actuator, the stroke is limited. A motor has an unlimited stroke. It can run multiple. It's only limited by, we can put external limits on a motor, but it's not limited inside the motor, right? You understand? A rotary actuator, the stroke is limited by the actuator itself. Now we can reduce that by using what we call mechanical stops or variable stops, where we actually have something that the actuator hits the use. So you use a motor in your car locks on your door, but it's got a mechanical, it limits the motor on the outside, right? You understand the difference. So when the door unlocks, it cuts the power off to the motor and also stops it. But no limits of rotation. So a rotary actuator, it rotates to a limit, right? You understand that? And this is done by the mechanics inside the actuator. So odds are I've never seen a rotary actuator that would do 360 degrees. Now I've seen it where it had a stop, but the problem is it hits here before it gets there and gets on the other side, right? But a motor has unlimited rotation. So over there, when we was looking at the manufacturing line, we had a rotary actuator that was on the first magazine. And you can see that you could actually hear that thing hitting its limits. So these are 3 types of actuators that we have. The section, and what we have is the control section. What we do is we use what we call control valves. They're called directional control valves, even though some of them do not actually control the direction. So you got valves at your house. What two things can you do with your valves? On and off, yeah. Now, of course, you can control the flow. Most of ours is that. So what we can do with directional control valves is we can turn the flow off, or we can turn the flow on, or we can control the direction, and that's why they're called directional. So if I've got what we call a double acting cylinder, we'll put pressure on one side to make it retract and exhaust the other, right? You understand? Or we'll do we'll swap the exhaust and the pressure to cause the cylinder to move in both directions. So these are directional control valves. And I think the next chapter is on directional control valves. So what we'll probably do, we want to get the lab. I know sitting in a lecture all day is kind of rough. But what we'll probably do is just get touching chapter 2 just enough to start in labs. And then we'll touch in chapter 3, which is cylinder. So the first lab we're going to hook up, of course, we're going to have a pressure source, right? Which is, we have a big shock compressor somewhere in this building. I don't know where it's at, probably downstairs. Yeah. And then we'll hook up a directional control valve, and we'll hook up a cylinder. That will be our first lab that we'll do. We'll try to look at that toward the end of the next class. So we'll be in lab, we'll be in lecture all day today. Yeah, so make sure you bring in your safety glasses, right? I didn't hear. Because we're not dealing with any chemicals. Huh? But no, we don't have an eye flusher here because we don't have any. I got one in my shop over there. So some of the components, filters and silencers, compressors. Anytime you compress or put a fluid under pressure, it creates heat. And anytime you compress a gas, it creates heat. So that means if we create heat, what do we need to do? Cool it down. So they put aftercooler, but that's not true. We have two types of coolers. One more I need to put in there. We have what we call an intercooler and then an aftercooler. So an aftercooler would be in the in the output side of the compressor. An intercooler would be inside between the stages of a compressor. We'll look at that later on. Separator, pressure switches, relief valve, tanks, also called reservoirs and receivers, lubrication maybe, filters, pressure regulators, directional control valves, actuators, and of course the piping. So we have our pressure source is probably not going to be located, it could be, but not real close. Even if it's located close to my actuators, normally your pressure source is away from your actuators. You've got to get it from the pressure source to the actuator. So this is where the piping will come in. And we'll talk about all this through the semester. Most of it is pretty straightforward. Are we okay? Not yet?
Why are women so stubborn?
Huh?
Why are women so stubborn?
I know some guys.
Cars are overheated and it's like digging out her, and I'm like, you pull over. No one's like you said. You pull over, I'm like, yes, you can. Call your dad. Still a car.
Okay.
He stopped on me.
Yeah, I know, literally. It's like, oh, wait, stop. Oh, that.
So y'all got any questions? Like I said, we'll look at these. Directional control valves we touched on a little bit. Separators. We run into separators in pneumatics. Because we got two problems with air, is that when we compress air can only hold so much water per cubic feet. If you reduce the volume of air, what's going to happen to the water? It's going to release it, right? And then plus you heat air up and then you cool it down. It's also going to release the water. We see that all the time. So we got to have something in there to get rid of the water. We'll talk about different ways that they do have methods of getting rid of the water in air. That's about it. In your compressor, you need it. Unfortunately, I'm one of the world's worst of not bleeding that off. You're supposed to bleed it off every time you use it.
What happens if you don't? Competition.
Well, rust, even though they do coat the inside of the tank with a anti-corrosive material, if you leave water there long enough, it's going to get into it and start controlling it. It starts to rust in the inside of your tank. So when it starts rusting the inside of your tank, then the tank will start losing its strength. And eventually what could happen? It could burst on you. Yeah, I would too. So yeah, I'll go out there over a month and so and drain mine at the house. Hydraulic power through liquids. Well, let's look this over. So hydraulics is a liquid, non-compressible. That's a term that we use, but that's not exactly true. It's just that it compresses so little. So it's almost impossible to get a fluid that doesn't have air in it at all, right? And of course, when we compress, air is compressible. So saying a fluid is non-compressible is a term that we'll use in this class, but the problem is it compresses so little that we don't even understand. So we couldn't measure the compressibility of a liquid. A very high power, precise position, and smooth motion. Now, what we mean by high power is that, of course, power is equal to force times how far something moves, right? So what's nice about fluids is we can put them under extremely high pressure. Of course, the higher the pressure, the more dangerous they become. Well, they don't compress. As far as we're concerned, we're going to say they're non-compressible. So what that means is that when I generate a area that this is pushing against, the force is generated into it. So they get a really smooth movement. Of course, this. What's that? Okay, so what we have, if we mix a liquid with a gas, then we get dispersion. But what we're doing is we're talking about a solid liquid, and even though there is a very minute amount of gas in the system or dispersed within the system in a fluid, we're going to just ignore that. And why is that? We can't measure, right? We don't have the ability to measure that. But if we cause things to happen, so let's say we don't have enough fluid in our tank, and we start moving all our cylinders, and then it drops down, and the intake on the tank is where, what happens on your bathtub if it's not stopped up and you open the drum? Gas swirl will come. Well, then you will have this problem. Then you will have compressibility if you really get true gas bubbles dispersed within the liquid. Cavitation. Oh, I don't know. For the replacement. So hydraulic systems are a lot more expensive to install. Why is that? Yeah, to install. Well, a hydraulic system would be a lot more than a pneumatic.
Oh, once you just get the part, you see that field system.
But not only that, so you're right, we have to buy the oil, right? High pressure, everything is such a high pressure, so what does that mean? All our tubing is got to be metal. You see very little flexible tubing. If it is flexible tubing, it's got to be high pressure flexible tubing. So I mean, if you go out there in your big air conditioner, you don't see any flexible tubing at all. Now your car, you have it. But that, y'all ever seen those flex tubing that's on your air conditioner compressor? You don't want to replace those things.
They're been too often.
No, because they're high pressure. So pneumatics is very, very cheap to install because just about all your tubing is plastic tubing. You don't see very much metal tubing in pneumatic. We run a lot lower pressures, which means it's safe. Hydraulic, you can literally shoot that oil into through your skin. I think I told you about it in the Navy when we got the shot. So it's fun. The big advantage of a hydraulic is since we use such high pressures, it means our actuators can be a lot smaller. So, what's the main formula? Force is equal to what? Okay. So what that means is if I come over here and solve for area would be equal to force over pressure. So what that means is the higher I can make this, the smaller I can make this, right? Y'all understand that? You get the same amount of force. So anytime I'm confined to the space that my actuators have got to occupy, then odds are we're going to use hydraulics. And rule of thumb is anything that requires an actuator that has to have over 3 to 4 inches of area, normally we consider hydraulic. Anything below that, normally we consider pneumatic. And what's the main reason on pneumatics? Well, the system itself is a lot less expensive to install, but pneumatics is not as efficient as hydraulics is. And we don't get quick response. Sometimes we get a jerky response. We'll talk about that. Because I've got an actuator using a compressed gas. Well, as soon as the actuator moves, then the gas is going to basically try to uncompress, right? And it's going to compress back. So pneumatics creates, if we don't do some things, creates a real jerky motion. Your actuators will move in jerky. Unfortunately, we didn't see that over there, but we got one actuator over there that's really jerky on the Festo line because it's pneumatic. But it still does its job. And we'll talk about ways that we can help eliminate that. So hydraulics requires a lot smaller cylinders, which means when your cylinders get big, of course hydraulic cylinders cost a lot more money, right? Why? Because they have to be able to handle that pressure. Because remember, that pressure is exerted all over the place. So if I've got 3,000 pounds PSI of hydraulic pressure, that means all my tubing is trying to push out on my tubing. It's trying to get out of everywhere, right? Let's go ahead and take a 2-minute break, guys. Rennelli's Law. This is on page 14 in the book. I'll have to add this to the PowerPoint because I didn't see it on there. Oh, wait a second. So Charles's Law. Let's find Charles's Law in the book. There's several laws, by the way, in the book. So let's look on page 9. This is Boyle's Law. So it's down in section 1.25. We got a book out? And I'll make sure he gets on in the PowerPoint, and I'll put him back up there. So there's several laws in this chapter that we need to make sure we go over that is not in the PowerPoints.
What time? Last week. Where were you last week? Where were you last week? I wasn't ready.
So this is in textbook, which y'all busy. So this is Boyle's law right here. I'm sorry, this is Boyle's law right. Oops. Oops. I'll get it in a minute. 1.25, Boyle's law. What does it say? You ever read that? Okay, so what's that telling us? Well, it says it's inversely proportional to its volume. That means if it, the smaller we can make the volume, the more pressure we have. The less the volume, the less pressure. So Boyle's law is what we use for a compressor. So what do we do to create pressure in a gas? We increase its volume. Volume. This is what Boyle's law does. Okay, so I need to make sure that gets. Then we move over to Charles's law, which is on page 10. So 1.2. So what does Charles's law state? Okay, so what that means is that things expand when they get hot, and they and when they cool, they do what? They
Except for
shrink.
what?
Except for water. H2O is really strange. When we freeze it, it expands, and when we boil it, it expands. So that's the only molecule I know that react like that. Everything else, though, if we chill it, it contracts, right? It gets smaller. If we get it hot, so that's what Charles's law says. And then the last law that's covered in here is Brunelli's. I guess that's the way you say it, law. And this is on page 14. States that if air velocity increases, the kinetic energy of the air also increases, while the total energy potential is energy plus kinetic energy if the air remains constant. So what does that mean? Well, it's saying the faster the flow, the more energy, right? So force is equal to air. So force is equal to area times speed, and that's what that's what it says. So that's why a hurricane, class 5 hurricane, knocks down a lot more stuff than a class 1 because of the velocity of air. Venturi effect is also, that's something that they cover that in this chapter.
I don't know about.
The Venturi effect, and this is right here, this is, let me bring my camera back up, which is not covered. So this is the Venturi effect, which is covered by Bernoulli's law, which says, okay, so what a Venturi does is we have a size pipe and then we deliberately narrow the pipe. And then we expand it back out. Well, what happens is when it moves, the velocity of the air goes up, right? You understand? Which causes what? That's not exactly true. I said that wrong. It creates, so Bernoulli's law says that the velocity increases, the kinetic energy of the air also then increases. If the kinetic energy increases, the total energy remains the same. Potential energy of the air flowing is reduced. Is a reduced flow of passage is reduced. So what they're saying is that the pressure on the sides here is less than the pressure on the sides here. So thank goodness, because this is what makes airplanes fly, right? You know what I'm saying? So what makes airplanes fly? The speed going across the top of the wing, since it's got further to travel, is less, creates less pressure than what's on the bottom, because it's straight. So that's why an airfoil is got, right? You understand what I'm saying? It's curved on the top. Yeah, and this is one way, over there on the manufacturing line, I'm sorry I got that wrong there, but over there on the manufacturing line, we have a vacuum generator, but we create it from a pressure source. But what they do is they do it exactly the way they show it in the book. So this is the way a vacuum generator works, is we bring in the flow here, then we run it through a Venturi, and then it expands back out. And right here is where we tap off the vacuum. Anybody that's got a pressure washer, you put a liquid on there. And that's all you're doing is you run that liquid into the side of Venturi, right? You know what I'm saying? And when you hit your pressure washer, when it goes to that Venturi, what does it do? It sucks that liquid right out of your bottle into your pressure washer. So you can add soap and all that kind of stuff to the pressure washer. This is what makes airplanes fly, right? You know what I'm saying? Because we make it go through basically a Venturi on one side. But what it has, it has to travel over the wing, the top wall, faster than it travels over the bottom, which creates lift. And that always amazes me. Those wings just don't look big enough. You know? When we flew over to Germany on a 330, you know, all that weight picked up by them little wings sticking up like that. Yeah. So I'll go ahead and add those laws to the PowerPoint for whoever teaches it next. They'll have it. So those are what's the 4 laws there. So there's 4 laws in this book right here. What's the 4 laws? Pascal laws, which is our basic fluid law that we're going to use a lot. Charles's law. I remember that because that's my first name. Boyle's law. So we okay? So that's chapter 1. So what's chapter 2? Yeah, control valves. So we're going to look at this and probably get through this chapter, and then we'll touch on cylinders. We'll get started on cylinders so we can do our first lab next class. Oops.